Thank you for coming. I'm going to talk a little about my ideas about Prolog. I'm not a Prolog programmer in my professional life, so my understanding of Prolog is more theoretical than practical. And bearing that in mind, I'd like to start with a very quick overview of how I view programming languages. So programming languages come in 4 flavors: imperative, functional, logic, and constraint. And these are the paradigms that we choose, and other things like objects, type systems, and so on, I would like to view as features on top of that paradigm. So I put a quick overview of that. I'm sure you're familiar with Fortran and Lisp. I would like to highlight that programs are very different objects in all these models. So in the imperative, programs are lists of commands. In the functional, programs are expressions, like mathematical expressions. In the logic programming, there aren't any commands really, and there aren't, well, in the pure logic programming, aren't any expressions. They're only predicates. And programs are sets of predicates. And the goal is to prove something. And in the constraint paradigm, the program is a set of data and constraints. And constraints determine values of some unknown parameters. So data gives some part of the parameters, and constraints specify other parameters. So in the constraint paradigm, there aren't any expressions, there aren't any commands, and aren't really predicates, because they're constraints that look like predicates, but they are specific to a domain. So in tech, for example, we give text, and then we give constraints about how to format it on the page. And in some GUI systems, you specify windows and you specify certain constraints on windows, such as how they are resized or how they are sharing the screen space. So you specify some data and you specify constraints on unknown parameters. And the specific solver should solve this for you. So from top to bottom, the task of the compiler is progressively more complicated. So I don't want to dwell on this for a long time, but this is basically, so I'm going to talk about the logic programming. Sometimes one hears that Prolog is declarative, and that logic programming is declarative. And also sometimes one hears that other things are declarative. So I'd like to propose a definition of what is really declarative and what is not declarative. And my definition is that declarative is when specifications are programs. So I try to make it more formal, but basically you need to understand a certain application domain. You need to understand how to write specifications for problems in that domain. You need to understand that pretty well. So what is the language for specifications? You need to understand that for each domain. Then, if you can map the specification language somehow syntactically to a program, that's declarative program. If you just map syntactically, if your specifications can be blindly transformed into programs that are actually executable and implement the specification.
Syntactic transformation from a visual specification formalized?
Well, you have to specify the visual in some way. So you need to understand what is your specification language.
Visual, I guess let's assume that your target language is one-dimensional, basically. It's a string of characters. So, as long as the specification formalism is also of this kind, I don't see a problem in principle, but if it is 2 or 3 dimensional, I don't know how I would do it.
Yes, I don't know also how you do it, but you have to do it. If you don't do it, you won't get declarative programming here. That's all. So that's all I'm saying. So if you devise or invent a three-dimensional programming language where programs are three-dimensional, maybe that will make you more happy. But basically, that's what you have to do.
Do you have two-dimensional programming?
So to take home, a declarative language is a perfect domain-specific language for your domain. And it is going to be specific for your domain. It's not going to be universal for all domains, perhaps. So here's an example, Fortran 77. It's a perfect declarative language for the domain that consists of mathematical expressions. So for example, I have a mathematical function here that is given by mathematical formula. The formulas are a perfect specification language. Mathematicians have figured out how to do that. We know everything about them. And you just transform this formula into Fortran code, and that's it. You don't write cumbersome register allocations or memory allocations or garbage collections or anything. You don't write segment offsets. You don't test that the brackets were read correctly. You don't test any of that. You just write a specification and it just works. That is what declarative means. So Fortran is perfect for this domain. Now, once you get a domain a little bit more complicated, that's not working anymore. So for example, here's an example code that I got from Wikipedia, dating from 1987. It's not anymore anything like this mathematical formula. It has labels, do loops, 2 of them. It's not like a formula anymore. So it is not declarative. According to my definition, this is not declarative. Haskell. Yeah, some people say Haskell is declarative. The definition that I'm proposing requires you to say what is your application domain for the declarative language. So I think application domain is basically algorithms on recursively defined algebraic data structures, such as trees. This is perfect for that domain. Here's an example. I take example from algorithms in C. Now here's a screenshot from the book. A binary tree is either an external node or an internal node connected to a pair of binary trees, which are called the left subtree and the right subtree. Here's Haskell code. Now, obviously, this is one-to-one. Now, I'm not going to explain that code. I expect you all to understand it. This is declarative. Another definition from the same book. How do you compute the height of a tree? It's a maximum of the levels, and the level is 1 higher than the level of its parent, and the root is at level 0. So we just write down that the root has height 0, and a vertex has height 1 more than the maximum of the heights of its nodes. That's it. It is declarative. We have translated the definition from the book verbatim into code, and that code is actually executable. Okay, now let's take another application domain. Okay, we're downloading some data from a web server. Now, I don't see where we're doing this here. Okay, I understand that this code will take me half an hour to get through. It's fine, but it's not declarative. It's fine, but it's just to illustrate what is declarative, what is non-declarative. I want to dispel this idea that a language by itself is declarative. It's not. I don't think that's true. I think it's always with respect to an application domain. So here's a little illustration of Prolog. So let's suppose we have a logic puzzle. I put this logic puzzle in red. This is something you might encounter if you're going into logic puzzles. So all jumping creatures are green, all small jumping creatures are Martians, all green Martians are intelligent, Ngturks is small and green, Pugvdurk is a jumping Martian. Who is intelligent? Now, the names of these characters come from Stanislav Lem's novel.
Is that where comes the dearth of vowels?
Yeah, they are aliens. So.
Yeah, but even Lem would have few vowels in his word.
But they were bad aliens.
Okay. Even fewer vowels.
Yeah, so and here's a program in Prolog that solves this question. So I say small Ngturks, green Ngturks, Martian Pugvdurk, jumping Pugvdurk. Now, the statement that all jumping creatures are green is written like this: green X if jumping X. So it is written a little right to left. So if you want to prove that X is green, then it is sufficient to prove that X is jumping. So it's if, you can read this colon dash as if. And so we rewrite all of these statements just like this. All small jumping creatures are Martian. So if you want to prove that something is Martian, it is sufficient to prove that it's small and jumping. Okay, and then we say who is intelligent. So we say intelligent X, and then print X. And then here's how I compile this program. This is literally what is in the file. There's nothing else. I compile it and I get the answer. So obviously, this is declarative for the domain of logic puzzles, or at least this kind of logic puzzles. Let me give an overview of Prolog. So it has logical predicates. So what are these green and jumping and so on? These are predicates. That is, you can think about it as a function that evaluates to true or false. But actually this is more than that. But at the first approximation, you can think it's just a function that evaluates to true and false in principle. So all other lowercase symbols that we have in the program are just constants. So let me show you again the program. It has the lowercase symbols Ngturks and Pugvdurk. I never defined them, so they're just constants. They're symbolic constants. They're not evaluated to anything. They just stay there. Since we didn't define anything for them, they're not predicates. Predicates are small, green, Martian, jumping, intelligent. And capital X is a variable. So anything that is capitalized is a variable. It's a logical variable that is implicitly quantified. And if it's on the left, then we imply universal quantification. If it's on the right, we imply existential. And so, for example, green X if jumping X, it means for all X, jumping X entails green X. So here, actually, since this is behind the entailment, this is existentially quantified. And another example would be this: path AB if path AC, path CB. It's a typical thing that computes paths in a graph. So we can translate this as for all AB. So AB are on the left, so they are quantified with universal. And C is free on the right. So C is quantified existentially. So then for all AB, there exists C such that path AC and path CB hold. And if this is true, then path AB holds.
So the idea is really, where is the variable introduced?
It is never introduced. So it is just used. Whenever you write a new variable, it is available.
But I mean, what is the distinction between A and C for this purpose? A appears on the left,
right,
but not on the right.
Exactly. So C is...
I'm sorry, A appears on both.
Yes, A appears on both. C appears only on the right. So C is quantified existentially on the right.
Okay, so when you say LVs on the left imply A, you mean
Sorry, what?
LVs on the left imply for all.
Yes. So if you introduce here new LVs,
Yes.
they're quantified with for all. If you introduce a new LV here, it will be quantified existentially.
Okay, so that's the point. Where is it introduced?
That's true, yes. It is introduced. So we will see how that works. And this is just, main is just the predicate that I put into the compilation so that this is the main thing that is to be evaluated when the program runs. So basically it's a query. And this query, since x is introduced on the right, it is existentially quantified. So basically it means we need to prove that there exists an x for which this predicate holds. Now, how do we do that? Well, let me show you the example. Right. So we prove existence of x by backtracking search. Here's a trace of this program. So first, we want to prove intelligent of x. So how do we prove intelligent of x? We have a rule, and the rule is that we prove intelligent of x if we prove that x is green and that x is Martian. How do we prove that x is green? Well, we look at what is given to us. Who is green? Well, Turks is green. Well, fine, we've proved that x exists and x is green. So x is Turks. Now we need to prove that Turks is Martian. So here's what it is. Green Turks. We have proved it. Exit. So we proved it. Now we need to prove Martian Turks. How do we prove that? Well, we're not given directly that Turks is Martian. And we know that Martian is true if somebody is small and jumping. So let's see if Turks is small and jumping. Okay, small Turks, yes. Jumping Turks. How do you prove that Turks is jumping? There's nothing except one fact about the jumping Pugvadurk. There's no rule to prove jumping from anything else. We fail. Fail jumping Turks. Fail Martian Turks. We go back, redo green somebody. So we are back here. We need to have another x who is green. Because we were here proving intelligent x, and we were too quick to grasp on the Turks. That was a bad idea. So who else is green? Well, we can prove green if somebody is jumping. Well, who is jumping? Pugvadurk. Jumping Pugvadurk. Now, we have green Pugvadurk because it is jumping. So then we have Martian Pugvadurk, and then we have green and Martian, and we have intelligent Pugvadurk, and we're done. So we are doing a backtracking search through all the available rules and facts. Well, facts are rules that have no conditions. So
how do we know we've done?
We are given the query to prove that there exists an x such that intelligent of x holds.
So as long as we find an existence.
One existence, x is done. In principle, there are commands to find another one if possible. But this is the same thing. So we know when we made the last fork in this search. We always store that place. And if we want another one, we go back to that place and find another fork. So this is basically, the proof may fail or it may succeed in more than one way. And we don't know that in advance. We just run it and we see what happens. That's how it works. Now, it's very important to see that the variables such as x is assigned, but on backtracking it is unassigned. So once it is assigned, it is immutable. So once we get x Turks, which was wrong, but we didn't know that, it is x equals Turks everywhere. We cannot change that anymore. So it's an immutable variable, but it can be unassigned. And then it's again free. It is not assigned. It has no value, waiting to be assigned. And the way it is assigned is called unification. So I will talk about this a little later, briefly. So the logic side of this, very briefly, is that we only consider predicate logic with a very restricted set of formulas that we allow. And the formulas that we allow are all of this form. They're called Horn clauses. And they're of the form conjunction of something entails something. There's never any other form. There's never conjunction entails another conjunction. Or not something entails not something. No, it's never like this. It's only this pure form. And then we have, sometimes we can have this. True entails something. We can have this too. And that's it. Now, disjunction, in principle, we would say, well, what if we want disjunction? It is not necessary to have disjunction because it can be expressed like this. A or B entails C. It's the same as A entails C and B entails C. So we don't need disjunction in principle. We could have it. We don't need it. And we allow only universal quantifiers on the outside of the entire formula. We don't allow any quantifiers inside at any place if they cannot be put outside. That's it. So that's the kind of formulas that we allow. And the way we solve this thing is called resolution. So if we have two clauses such that one and the same predicate is here on the left, here on the right, then we cross them both out, and the result is C if APQ. Now this is a logically valid inference, and this is the only inference we do in this procedure. So actually, the only question is which pairs do we select? Which pairs of clauses do we select where one and the same predicate appears on the left and on the right? So if we look again at our Martian's code, you see resolution, for example, here. Intelligent X is green Martian, green is jumping. So green here is on the right, and here is on the left. So we cross out green, and we get intelligent if jumping and Martian. And then Martian is small and jumping. Again, we cross out Martian, we get intelligent if small and jumping. And then we get small and jumping, and we're done. So that is kind of, so the only unclear part here is which clauses we select. Do we take the first one, the second one? Because there are many of them that have the same thing on the left and on the right. So the strategy here is depth-first search, usually. And it is just going in the order of clauses as written in the program. So you can see I was able to confuse it to select negaturks first, which was the wrong idea. But I was able to force it by putting it as a first clause. So it actually starts with the first clause and then goes depth first. So in this way, it works. So Prolog, core Prolog is only this and just this. There's nothing else than resolution. Well, you might ask, how do I compute a factorial or a Fibonacci number or something? Right? Now you compute that in a roundabout way. You cannot compute anything. You can prove that a predicate holds. And you can prove that it holds when there exists some number that makes it hold. So let's define fact of NF, which holds when the numbers n and f are such that f is equal to n factorial, and in no other case. And let's now say, well, factorial of 1 and 1 holds. And factorial of n and f holds if this is all true. So we say m must be equal to n minus 1. So factorial of m is equal to e. Factorial of, and f is then equal to e times n. So these things are a little roundabout, but this is necessary because we only have predicates in the language. We don't have equations or functions or expressions. We do not have functions or expressions in this language at all. So we only have predicates, and so Fibonacci does in the same way. It's kind of cumbersome because you have to go one step by one step. You cannot just write an equation. But it works. So, very important also, this is not an expression. It looks like maybe an expression. It is not. Actually, it is a predicate is that is infix. And it is applied to arguments m and a data structure. So this minus actually doesn't do anything. It is an infix constructor of a data structure. It is completely passive. It is just a data structure with two values inside, labeled by minus. And so this is a predicate. And this predicate is defined in a special way so that it knows about minus. But
it knows what?
It knows about minus. It knows that if it sees a data structure with a minus in it, then these two better be numbers, and then it can subtract. It's a built-in predicate in the system. So you cannot define it in Prolog without a huge amount of effort. So this kind of thing is a predicate that will force M to be unified with the result of this computation. But for you, this is just a bunch of predicates and data. So now we get to a very important part of Prolog, data structures. So this is actually a data structure. It is passive. It is not evaluated. Let me show you data structures. If you have a predicate-looking thing that is inside a predicate, then it's a data structure. That's the basic idea. Prolog has the syntax for data structures that is the same as the syntax for predicates. Just, for example, pair of xy, you can write that. And pair of xy that appears inside a predicate, so like in this code, left of pair xy is x. Since it appears inside a predicate, it must be not a predicate itself, it must be data. Because inside predicates, there cannot be another predicate. So then there's no need to declare anything, you just write it like this and it just works. Questions?
Inside a predicate, you cannot have a predicate.
No.
If your predicate is, and you're trying to show if two booleans are equal, you can't use other predicates as the argument?
Predicates are not booleans. They do not evaluate to anything. They are special, they're booleans, but they're special booleans that you do not manipulate yourself. They tell the system what to do. And so you cannot evaluate them just like that.
So somewhere other than Prolog, are there higher order predicates?
Yeah, yes. Well, there's higher order Prolog also.
Oh, okay.
But people have done a lot of research on this. People have done all kinds of things. Yes, so there are second order logic programming languages and all kinds of stuff. Yes, but I'm not going to talk about this. So another interesting thing about Prolog is that it has syntax. It has user-defined syntax that you can define operations like this if you want to do postfix factorial or whatever you want. You can have associativity indicated by these keywords and so on. So there's syntax sugar for lists that looks like this. So I'm sure you've seen this somewhere except for the bar. You've seen this syntax in some language. So, for example, to compute the head of a list, we write a predicate that looks like this. So what does it do? It says the head of something and something holds when the first element of the list is the same as the second argument of the head. So in other words, if you want to compute the head, you just say head of list comma x, and then x will be forced to be the first element of the list. And if there's no first element, then this whole thing will fail. And then you will backtrack to whatever you did before. And the same as with tail. So tail is a list that we normally would see it's here. So if you want to compute tail of some L, then you write tail of L comma x, and then x becomes the tail. And again, if it's empty, then it will fail. So empty is true on the empty list. In this way, you can check that this is empty. So then, for example, here's how you define length. You define length in this way, and it looks very much like pattern matching. First, you have this length of 0 for the base case, and then length is incremented if the list has a head. Now, I want to ask you, which programming language has this kind of idea of how to define length? ML, Haskell, right? Now, I'd like to say also that Prolog was invented in 1972 at the same time as the C language. And it had all these things. This is very interesting. Now, just one word about unification. I will not say very much, but basically, it's a way of assigning values to variables in Prolog. It is always done by pattern matching. For example, here's a program that says, like yx is like x and like y, and really AB is like A, like AB. So the predicate really 1, 2 holds. How does it compute? So really AB is like A and like AB. So really like A goes you into like 1. And like 1 holds by fact. Okay, so we go on. A is 1. Once you get A is 1, then A is 1 here as well. It's unification. Rather, it's immutability of the variable. So once you have assigned this variable, it is immutable. So here must be 1. So like 1b. Like 1b is unified with like yx. So y is unified with 1 and x is unified with b. And then you're like 1 like b. So it's like b like 2. Like 2 holds.
X and Y must be distinct?
No.
Okay.
But at this point, you have like, AB is like, 1, 2. So like, 1, 2 is like 2 like 1. And like 2 like 1 holds. So you have to unify like, YX with like, AB. So you have to find out which parts of these structures are known, which are not yet known,
yes, and
assign them. And this is what Prolog does for you automatically. Yes?
In this case, could you have both x and y be 1? Or like 1, sorry? Or both x and y be
like no. Like, 1, 2 is only forcing you A equals 1, B equals 2. So then this can be unified with like, YX only when Y is 1 and X is 2. So there's no, in this case, I did not leave any freedom. I could ask really 1X, and then you would unify it with other things. Or really 5X would fail. So unification is basically this idea that you have a structure with some pieces fixed and other pieces not fixed. You have another structure also with some pieces fixed and other pieces not fixed. And the Prolog system finds out which variables can be assigned to some structure so that the whole thing matches. So this matching is basically pattern matching. And this is done for you by the system. So you do not, you just write things like this and they just work. Okay, so now let me go to an interesting subject of pointers made safe. Here's an example of how you append two lists together in Prolog. I call this L append. This is a standard thing that you would do. You append empty list first, and then if it is not empty, it has a head. So the result must have the same head, and then you append y and the rest, and you get z's. So that is the way you append the list. And this is O of n, because you have to go through each element of the list. And you would like to optimize this, and to optimize, usually you would say, I want a pointer to the end of the list, so that I can just assign it there, and that will be constant number of operations. So in Prolog, you cannot have pointers, but you can have a funny thing. A part of data structure can be a variable. It can be this logical variable that is not yet assigned. It is free. And so this is like having a pointer to that place in the structure. So the solution is that we introduce a free logical variable and unify that logical variable with some part of the data. So here's an example. We take a pair of a list that has a free variable at the tail and that free variable. So it's a pair consisting of two Prolog terms, one being a list and another being just a free variable. And this is important. It's the same free variable as at the end of the list. There's another syntax for this with the minus. Now, I remind you that minus is not arithmetic in Prolog. Minus is a data constructor that is defined syntactically as an infix operator. It doesn't do anything. It doesn't compute anything. It's just a passive data constructor.
So we're using it to hint at abstraction before, but
Yeah.
now something else.
Well, we kind of suggest that we take ABCX and we subtract X from the end.
Okay.
So that actually it's ABC that we are interested in, and X just plays the role of a free pointer at the end.
I'm sorry, the syntax A comma B comma C
Yeah.
bar X.
This
What's the head of that list?
A.
All right,
So bar is just like a cons in Lisp. So
all right.
it's just a pair of something and something. So A is the head, then BCX is the tail. Of that, B is the head, CX is the tail, and so on. And this X stands for the rest of the list. But it is unassigned. It is a fresh logical variable that is not assigned.
Fresh.
Yeah. Well, fresh in the sense that when you use that, you want to put it there usually as a new variable, so that it is not yet assigned.
They use the word fresh in Unification, right? To introduce a little bit.
Well, yeah. So
Is that related?
fresh is used in many contexts to introduce a variable you haven't yet used.
Okay.
So, okay, so these are called difference lists in Prolog. These are really just lists with a free unassigned variable at the end. So how do you use that? Well, here's, for example, how you append two difference lists. It looks cryptic. So how does it work? Suppose we want to append ABC and DE. So first, we use not just list ABC, but we use a difference list that has a variable A at the end. We use DE with B at the end. So when we say DL append this, C, we say C must be this appended to this. So how does it work? Well, X minus Y, Y minus Z, X minus Z. So what is C? It is X, but we don't know what Y really is. Let's look at what happens here. So first, we get this thing, G2456, and this thing is replacing B. So this thing is replacing A. Now, the next step is that G2456, let's see. So let's see. So the next step is that we get x minus y. Now see that x contains this 2447 that has disappeared. So what is now 2447? It is d, e, and the rest. Because you see this a here must be equal to this. So actually the system says I can unify this only when a is equal to this. So then I have this list, A, B, C, capital A. So it's like this. So now we get A, B, C, D, E minus D, E. Now this is still the initial list, right? Because we subtract D, E. But we have now the head, which is A, B, C, D, E, unified with X. So the result is that there is this free variable at the end, so C becomes A, B, C, D, E with a free variable at the end. So the system magically finds what is the unification necessary to fit this formula into the data that we gave it. And the key is that this A is unknown. It can be anything. And so this A actually becomes DEB to unify that. So because if A is DEB, then we can unify this Y with this Y. So we have to unify this A with this DEB. And that's the only way. I should have explained it. Well, I should have replaced this output with readable names. But basically, the idea is that this needs to be unified with this. And this can be unified in only one way, when Y is equal to DEB. And so, since Y is also equal to A, so then A must be equal to DEB. Once you get that A equals DEB, you're done. Because then this becomes ABCDE, and this becomes ABCDE, and you're done. So we have unified in constant number of operations. So basically, the fact that we have a free variable at the end of the list allows us to set a value there and append to the list. And this then is used to implement queues. So for a queue, you want to insert at the end and take from the head. So this is, again, constant operations. You insert at the end like this by saying, well, I insert E at the end of some queue, and I get a queue that has E inserted right at the end of this queue here. So this is how it works. Again, it's the same unification that forced us to identify the end of the list with this. So now the end of the list is identified with this. And so we have appended to the queue in constant number of operations. So this is how these things work. Yes?
Does this in effect some kind of memorization?
No. There's nothing to
I'm not clear about it.
So let us go back here, maybe. So I think that the easiest way to see it is to look at the first line and to compare it with this. So the system is trying to find x, y, and z that match what we have written.
Yes.
What are they? So let's start with y. Now, y is after the minus and before the minus.
Yes.
So after the minus here is a, and before the minus here is DEB.
Yes, yes.
So obviously a must be equal to DEB. Otherwise it doesn't match. Once a is equal to DEB, now what is what is B? Well, let's see. B must be at the end of A, B, C, D, E. So it remains free. Now what is C? C is x minus z, and x must be that which is before the minus. So x must be a, b, c, d, e, b. So the easiest way to see it first is to look at the y. Y must be equal to d, e, b. And a, therefore, must be equal to d, e, b. So what is then x? X is that which is before the minus, which is a, b, c, d, e, b.
Yes.
So x must be equal to a, b, c, d, e, b. And then what is c? C is x minus z. So a, b, c, d, e, b minus b. So it is basically done in one step by the system because it's just unification of what you have written.
So
Yeah.
when we talk about unification, it seems like this is a very abstract thing that's kind of combining several different possible cases, one of which I would imagine, and you can tell me if I say something wrong here, but one would be sort of like a searching whether you can find a something that fulfills a function composition. Another one would be searching for something like a monadic followed by, and another one would be searching for something like the result of an Aristotelian syllogism or something.
Well, this is all.
And this is some kind of general abstraction that comprehends all of those.
Yeah, the abstraction is that you have these data structures that are recursively built, and they're just passive symbols. So, for example, x minus y is a passive symbol, is a pair of x and y labeled by minus. There's no calculation there. So, and you can nest these to any depth. And on the top level, there's a predicate, but behind it, below it, there are these nested structures that can go to any depth. And so then the free variables must match the places in these structures that match. So minus must match the minus. It's a constant. So whatever is around the minus must match. And a comma is a separator. So whatever is before the comma must match. Whatever is after the comma must match. And with this mechanism, everything is done. The syllogisms, the monadic composition. I mean, this looks like monadic composition a little. Everything is done just with this mechanism. There's only one mechanism, and it does everything. So it's kind of a one tool for all jobs. That's kind of thing. Now, the last thing in this series of pointers made safe is iterators. So I want to have an iterator. I want to set it at the beginning. I want to increment, and then check that it is at end. So to implement it, we split the list into a pair of queues. So there's a queue before a certain element and a queue after a certain element. And since we have a O of 1 appending to end of queues and O of 1 taking the head, we can always, in O of 1, advance the pointer by putting the head of one queue to the tail of the other. And we can always check that the second queue is empty. So here's, I define an operator double caret that is just my fancy. And then I have two different lists separated by this. So basically it's a pair of two lists. And then if the first one is empty, then we're at the beginning. The second one is empty, we're at the end. And to increment, we just push this x from, oops, I think this is this must be, yeah, right. So this is at the end of the queue, and this is the beginning of the second queue. So we push that over there and unify. That's right. So when we say increment one iterator, comma another iterator, then the second one will be incremented from the first. So then I trace that, and you get, I increment A, B, C, D, E, and I get A, B, C, D, E. So again, in constant number of operations, I have taken one element from the head of one queue and put it at the end of another queue.
But you still have variables
Right.
in the bottom.
Yes, because I must have them, because these are the data structures that I'm working with. So the queue is a list that has a free variable at the end. So, and I must have access to that free variable. So I must have a pair of this list with the free variable and the variable itself. So this pair is always present. So this free variable is always apparent.
So the quote-unquote answer is the left side of this structure.
Well, no, in my notation is the right side that is the answer. So increment of this is equal to this. But it is just convention. So since it's a predicate, it does not say what is being computed. It is true when these things satisfy the matching. So it can be used in both directions. I can increment or I can decrement. But actually, no, actually, I shouldn't say that. Decrement doesn't work, because then you get a list that is not well formed. You do not have a free variable at the end. So this is kind of an iterator that only goes forward. So it's a single linked list where you cannot go back.
In terms of the iterator, what we're looking at in that last line where x is unified. Right?
Yeah.
We're saying that our cursor more or less is at C,
Yeah.
correct?
Right.
And then the first side, the left side is ABC,
Mm-hmm.
and the right side is DE, right?
Right. No, so A, B, C, D, E is a list,
Yeah.
and we have a pointer that points currently at D.
At D.
Well, sorry, initially it points at C, and then after we increment it, it points at D. That was the idea.
Have we incremented it when we reach the x equals line at the bottom?
So x equals is the thing that we had before incrementing, and now we have another one. Now we have point. So now C is at the end of this list, and it would not be difficult now to get it unless we had it here. So it is not easy to take elements from the end in this structure. It is not easy. That would be O of n to do. And so it is like a singly linked list that only goes forward.
Yeah.
But nevertheless, this construction is very much like having a pointer in the structure. So you can advance it, you can take the element at the pointer, and then you can, for example, chop off all the rest of the list if you wanted.
So I'm sorry to be a
Yeah.
pain, but you've given two examples where, at least from the naive point of view, it's difficult to see how you arrived at the predicates you wanted in order to...
Oh, how that was programmed.
Yeah.
Not easy. Very confusing. It is too brief, this thing, to be understandable.
I mean, is there a way to derive plist at begin, plist at end, plist incra? The appropriate ones for
Probably,
particular-
yes. I mean, you probably can do that. Yeah, but I don't
Where
know.
do they come from?
So, I mean, this is kind of
Does one just think about it?
developed intuition for this. This is, I don't know how you, this is not easy. These things are, so you think about this as a list where x points to the end.
Yeah.
So empty list means that the pointer also points at the beginning. Now you think about this as two lists that are kind of head to tail next to each other. So then what do you need to do to chip off the head from one and put it at the tail of another? So you kind of figure out how this should work. So this is the head of one, and this is the tail of another. So you put it in there.
Starting to see it.
It is not easy, because this notation is too brief. It is too concise. It is not so visual. And so at this point, I'm not sure that this is still declarative. Right? So this is part of Prolog that is very interesting, but So pointers do not seem to be very declarative in Prolog, but they're safe. What is interesting is they're completely safe in the sense that you cannot make a null pointer. A pointer always has a value that it points to. You can increment only if the list is not empty, and
so what's the direction again? Is the
left to right.
Okay, so the state we are going from is on the left?
Yes. So this is a convention in Prolog. So usually the ones that are on the left in a predicate are the input values, and stuff on the right is output. But with very tricky programming, you can do it reversibly. You can make predicates that can be used in both directions. For example, appending lists, you can say, what is the middle that you have to append to get a given result? And it will go through search one by one element to find what you have to append. If you are very careful, you can do it. I don't know why you would want to do it, but you can do it. And in principle, the language does not specify that this is output and this is input. The language just says the predicate holds for some values. Let's find them by search. And if it doesn't find, it's your fault. You would fail. Hopefully you would fail. I did not check all the corner cases here, but you should do it such that you would fail. And that would be the Prolog way of throwing an exception. Just the predicate would fail and backtrack to whatever you were doing before. Yeah, some implementations of Prolog have exceptions, but this is not... I'm talking about a pure core language that has only predicates and how you would do things with that.
Is it just safe if C is a free variable?
Yeah, well, it must be. Where do you mean? Sorry, what?
The last line.
Here?
Yeah. If
Well,
C is a free variable already.
Well, this is my program. So in this clause, all variables are free because they haven't been introduced anywhere. It's just that if I use this in some context where I already assigned some variables, then it will be not free. So let's say, X is true if increment blah blah and blah blah and blah blah and blah. So if I do that, but maybe some of the variables have been already assigned when I get to this predicate in the chain, and so that is, you have to be very careful to know what is already assigned and what not when you write Prolog. So that is the kind of, see, my programs are very small, and so it's not so clear where the problems will be, but they will be there. So another thing that is kind of funny about Prolog is that the evaluation strategy of Prolog is very similar to top-down parsing. So if you consider top-down parsing and you allow unlimited backtracking, then it's basically the same strategy that Prolog uses when evaluating your clauses. So that means a top-down grammar, so a grammar that is good for top-down parsing. So here I do not have left recursion and so on. This kind of grammar will be translated syntactically into Prolog, and it will work. So this is another area where Prolog is declarative. So here's what happens. Suppose I have a very simple grammar, so I have expressions that are terms, operators and expressions, and then and or are the possible operators, and true and false are the possible terms, let's say.
So I guess this is why Prolog is used for natural language?
Yes, for parsing. Well, I will talk about it a little more, but yes. So you just write, you consider a queue of tokens where you can add tokens at the end, and you can get tokens from the head. And then you define, for example, that expression of this queue is that first you have a term, then you have an operator, and then you have an expression. So this is directly translated from the grammar, except you have to add these things to represent the queue of tokens that you consumed and not yet consumed, and so on.
Ah. So that list thing is usable in many contexts.
Yes, of course. You see, this is just an empty passive structure. This minus does nothing. It does not evaluate to anything. It is just like a pair with a different syntax. So you can use it in any context you want to represent a pair if that is convenient for you. And it already has functions, but basically it's here we just write it like that. And so there is syntactic sugar with this funny arrow that is provided in the Prolog so that you don't have to write these things. They will be implicit. So then this is what you write. This is just a grammar more or less like that with a little syntax. And then you, for example, you ask, does it parse expression of true and false or true? Yes, and this will hold. This will not fail. Now, obviously, parsing, so this is called definite clause grammars. I don't know why. What would be indefinite clause? I don't know. But this is called definite clause grammar. This syntax. And also, you see, this is a purely syntactic transformation from here to here. So in fact, we can have more arguments here in predicates. So we can have parameters on the grammar non-terminals and also on terminals. So we can have augmented grammar that have attributes on all terminals. And we can check that they fit in some way. So that means we can parse non-context-free grammars, at least some of them, by using, I'm not going to show you that, but imagine that here I can have arguments in this predicates, and expression needs to find a variable, and it will be pattern matched and so on. And so I can parse natural language by saying, this is a noun phrase with masculine gender, and this is an adjective with masculine gender, and only when they match, then this parses. So this is a kind of grammar with attributes. So inspired by this, people tried to use Prolog for natural language processing. So again, so this kind of thing is built into the language. Interpreters. Yeah, interpreters, somebody already mentioned, is very similar to what Prolog does. Here is my lambda calculus interpreter. It doesn't really work, but it's kind of working to some extent. So what it does, it defines the two constructions of lambda calculus, the lambda abstraction and the application. And then the comp is the predicate that computes. So the left is computed to yield the right. So the lambda is computed to itself. And application of lambda is computed like this by unifying the variable here with the argument. And then if I have a double application, I try to do something like this. So I compute first one application, then I compute another application. And when nothing works, then I don't do anything. I leave the expression as it is. Okay, so actually this works in quite a lot of cases, like this, for example. This is a constant function that I apply to 1, and I get a function that takes y and yields 1. Many simple tests pass, but more complicated tests fail. So basically, I get bad things like this, where a variable is identified with a structure containing the same variable. And then when I get this, then the whole evaluation gets stuck. So I did not handle alpha conversion. I did not rename variables. This can be done in Prolog, but it needs much more than just 2 lines of code. But basically what I wanted to show is that it's very kind of convenient to organize an interpreter. It's very much less work than it would be to write an interpreter in C. So I found, this is a link that you can see in the PDF file that defines a module that does actually lambda calculus more fully, so that you can define the Y combinator, factorial function in church numerals, and things like that. I don't claim to understand how this works. I looked at this module. It is not long, but it has some hacky aspects, so I don't want to say that I understand how that works, but anyway, it's easy, much easier than in other languages.
Question.
Yes.
So you showed some examples where you're saying that this unification mechanism can kind of do some list operations and solve maybe sort of some non-CFGs. Are you making the claim, or is there any theoretical stuff that says, I mean, you're not saying that this process can do any sort of Turing computation, right? I mean, or is this known? Or?
Which process? Well, it is Turing complete.
I mean, can you like, if you nest this stuff deep enough, are you trying to claim that you can basically solve anything that's computable, or
yes.
Is that theoretically known?
Well, yes. I mean, the Prolog module of computation, this is what is called logic programming, is Turing complete.
It's Turing complete.
Yes. So I just showed particular applications for parsing, but you can compute any recursive function, and well, I showed the primitive recursion basically, and also arbitrary recursion, and yeah, you can. It is not restricted, this model. Now, if we restrict ourselves to Prolog programs of a very strange kind, where you have only facts, suppose we have facts that different people lost different things on different days, and if somebody loses on Monday, then it's unlucky for the whole week for that person. So who is unlucky for the whole week and also lost something on Tuesday? So that's my question. And if I want to answer this question, I write a Prolog program that says who lost what and when. And then I define unlucky, like this. And then I define my query. So who is unlucky who also lost something on Tuesday? So obviously, right? Obviously, this is declarative for this kind of problems. I translated English into Prolog just like that. So now this works. It gives you the result, who was unlucky. Note this syntax. I'm sure you've seen some other programming languages that use it. The variable that you don't care about. So now, if our predicates are either facts, like lost, or they're non-recursive inferences like this from lost, then we need no backtracking. We can just compute this without backtracking. If we don't find facts, then we failed. If we found facts, there's nothing else to do. So, and the query will usually return many results. So there's a special subset of Prolog that just solves these kind of problems, where you have either facts or non-recursive queries that return many results. This subset of Prolog is known as SQL. So we have seen this before, right? There's a table. So these are the facts. Now we create view, select person from lost, blah, 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 blah. Select person, natural join, blah, 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 blah. So basically this Prolog program is translated into SQL more or less syntactically with a lot of noise, but still. We need to introduce names for each argument that Prolog just writes down. We introduce names, person, day, object, right? And then we select and we say natural join, so this is comma here, right? So this is comma here, and the fact that who and who are the same variable, this is natural join. And then where, again, so there's a where built in here. So this is SQL. This is a certain narrow subset of Prolog. People have also invented data log that has recursive queries, but it does not have recursive data, like lists and so on. So it's, well, SQL has been growing very much, and it has all kinds of features that Prolog doesn't have, such as functions, limited, of course. It has typed values, has named values. So people thought, well, SQL is kind of ugly. Let's just add these features to Prolog. So let's add functions, typed values, named values. We'll do that. Yeah, and that is Mercury. So this slide is a little, oh, this slide is out of order, sorry. It is how you compile Prolog. I will show it later, maybe if I have time. So if you add these features to Prolog, you get basically a language that is called Mercury. It has all the features of ML that you care to name, plus type classes, and it is purely functional. It has some interesting things. For example, it detects errors in how you use your predicates if you don't have the right types, if you don't have the right modes, and so on. So it checks which predicates are deterministic, which are non-deterministic, which can return many values, which can only return one value. It's all statically checked based on types and so on. It has modules. It has all kinds of things, and you can compile it to high-performance code because of this. So here's an example. Of course, it now looks much more noisy. To compute the factorial, this is basically how you compute the factorial. It's a predicate, but this predicate contains now evaluated expression. So this is now an expression. This is evaluated. This is an expression. This is evaluated. This is not anymore a predicate. The compiler knows that this is a function. It does not need any backtracking. It does not need any unification. It can be just compiled into machine code. And it does that. So judicious use of functions at the right places speeds up the programs. And so this is basically very similar. And then you have a lot of noise that comes from the fact that everything needs to be declared, that everything needs to be moded. So for example, what is main? Main has two arguments, which are destructive input and unique output. So these are linear types, in fact, that are used for input-output. So these are types such that you can have only one variable, only one value of this type. Once you use it, it's gone. So the syntax sugar with this bang IO, that is the uniquely linearly typed variable that kind of is monadically passed from one to another. So this is kind of a syntax sugar that looks weird, but basically that's what they use for input-output. So you have each input-output operation has a token that it receives from the previous operation. It can be used only once and then it's gone. So you have another token that you pass to the next input-output operation, and each of these tokens is linearly typed. So this is how they did input-output. So then you say that main is deterministic, so that this main does not need any backtracking. It just computes one value and finishes. Predicate factorial is deterministic and has an input argument and output argument of type integer. So you define all this in detail, and the compiler will refuse to compile if you do anything else then. So this kind of thing, you see expressions, you see functions, string.strip, the module defining a function on the string, and yet you have Prolog features such as unification. OK of string is a data constructor. So this is a data structure that has a string inside, and the result must pattern match against that. So it's kind of a wild combination of functional programming, logic programming, types, and it's way, way too complicated. to use.
It will be interesting to compare like the length of a non-trivial program, right? Because it does at some point the features do count. It will probably shorten the program.
Maybe, yes.
But
I'll be interested to try this. So far, I would say Prolog is a perfect scripting language. It needs no declarations. So everything that we come to associate with scripting languages nowadays is in Prolog. Everything. Every single feature that you think scripting language must have. No declarations, dynamic types, runtime types, user-defined syntax, pattern matching, meta-programming, reflection. You can do embedded DSL easily because you can redefine syntax, and you can do meta-programming. You can create predicates at runtime, put them into the system, or delete them from the system. So you can have this self-modifying code, so to speak. You can have external DSLs because you have easy parsing. So you can easily define a little language and parse it right in your program. There's a standard with many free implementations. Typically, they come with a REPL and a compiler to a high-performance virtual machine. Again, features that we typically associate with scripting languages, right? Interfaces to various external things like databases, networking, and so on. Databases, as I mentioned, they come with SQL. They're highly optimized for these specific operations that they do. So Prolog can just interface to them and do queries on an external store of facts without having to write them all in your program as facts. You just interface and do Prolog queries on that. So with high performance on that end, and then anyway, you can do all kinds of things, and the core language is small. It has only a couple of features that you have to understand. Once you understand these features, how these variables work, how the syntax works, that's it. It's a little like Lisp. It has very few features that really need to be understood. And then the full language, of course, is hard to use, like any scripting language. You have a big program, you easily make a mistake, you forget some order of variables in a predicate, everything just breaks down. The compiler doesn't tell you that you made a typo in the name of something, right? Because you make a variable that's called ABC, and then you make another that's called AB capital C, and that's a different variable. And it's fresh, and it's okay, you can use it. So just like every scripting language, hard to use the full language for big projects. But, let's see, what time? Oh, it's 8:40. Okay, well, I'm finished. I just wanted to show you this slide about compiling Prolog to a virtual machine. So this is an old document from '83, and the Warren was the guy who invented the first really good abstract machine for Prolog. So here's an example of appending lists. We have seen this example. It's recursive appending of lists. And this is the translation of this into virtual machine code. So you see this is very high-level virtual machine. It has instructions with symbolic terms, such as get list or unify variable, unify value. So basically this Prolog code is translated into the virtual machine instructions without very much work. And this was, of course, necessary at that time. You can imagine what kind of computers they had back in the early 80s and late 70s. And this was invented in the late 70s. So it was very important that the programs were small and that everything was small. And I mean, this kind of thing fits into 100 kilobytes or something. So yeah, so this is just to have a taste of a virtual machine that one uses. And of course, today people use very much more sophisticated virtual machine. But basically, the idea was this: that you make some kind of virtual machine that.
So when you show the trace of a search, that's basically a trace of this virtual machine, right?
Yes. Well, it was, of course, massaged into more readable form. Because the virtual machine has some stacks, heaps, it manages many things. It has very high-level instructions, such as unify variable. And that means many pointers need to be compared and pushed and whatever. And so that kind of thing is difficult. But the problem is compiling Prolog is impossible because it has to do the backtracking search. You cannot compile that unless you do the backtracking machine. And if you do the backtracking machine, you need this kind of machine. So basically, once you want to compile Prolog into something, then you're forced to invent a virtual machine that would do these things. And then, of course, all the features of the language come on top of that. I did not talk about many of the features, but basically, I wanted to give these take-home messages that, well, if you've seen Haskell and you've seen SQL, then Prolog would not be very difficult. Many features of Prolog live as its legacy in the languages we use today. Pattern matching on recursive data structures, this kind of backtracking search is, of course, unique to Prolog, but still we know how to do that. We know how that works. Parsing, people are very much in favor of this kind of top-down monadic parsing, which is basically the same as what Prolog already has. There are many projects, there are many variations on Prolog. People have studied exhaustively what you can add to it. Higher order logic. You can add functions, types, you can have higher order. These are actually polymorphic higher order types here that are added to Prolog in the Mercury language. So it's very complicated. The result is just, it's not clear how you use that language. Am I supposed to just use the functional part of it? Am I supposed to just use the logic part of it? It's not clear. Object-oriented Prologs, there also exist. Right, I mean, there are all kinds of extensions. And yet, I have a feeling that Prolog is basically forgotten. And so I wanted to, I don't know, maybe you have a different opinion. I have a feeling that today people rarely look at it, rarely do anything about it. Maybe computer science courses, but not all of them.
I know a professional Prolog programmer.
Yeah?
She works for Second Life.
Oh.
Wow. Second Life.
Wow.
That's interesting.
It is.
So what, do they do some kind of artificial intelligence in Second Life?
Well, she deals with errors and recovery from errors and handling user interactions around them. You know, it's not the main engine of the game, okay?
Right. The main engine is written in Haskell, right?
Of course.
Yeah. Who else knows some Prolog programmers?
I met someone who she was not working on Second Life, but in Second Life for a university program.
Wait a minute. Is that Annie?
Yeah.
That's her.
Oh.
That's the one person.
So
Okay.
is she
There's only one. We unified them. We unified.
So yeah, you have a more precise description of what she actually does. Yeah.
Okay.
Yeah.
She works in Second Life,
Yes.
teaching Prolog.
Although
He's designed an online avatar to fulfill.
I actually attended a Prolog class that she taught in Second Life, but that's not her main thing. She works for, I forget which university it is, but they have a program where there's basically tests and exercises that you can do in Second Life, and she scripts those in Prolog.
Oh, I see.
So
Scripting language.
The perfect scripting language, yes.
So when you said scripting language, have you done any of it?
No, I can tell you my personal encounter with Prolog. It was a while ago when I was still in Russia. I read a book on Prolog, the Kloksin Melish. I understood nothing. I understood literally nothing. It was a bunch of difficult, strange, unclear stuff. And who would ever want to use any of that if it was so unclear and it was poorly explained as far as I understand now? Kloksin Melish, I'm trying to figure out who that was, Kloksin or Melish, who couldn't write. But there's another book by Melish and another guy on linguistics. It's also not very well written. So maybe it's Melish, because Kloksin wrote good papers. So one of the papers I give as a reading list, well, you can see it if you download the PDF, is a paper by Kloksin on the virtual machine for Prolog that he invented. And that paper is reasonably well written. So I can't imagine that he couldn't write a book well. So I guess that was Melish. But anyway, it was a wrong book for the beginner. It was a wrong book. Prolog needs to be explained in a different way. My second encounter with Prolog was quite recent, several years ago, and I thought, wow, why didn't I see this before? You know, all these things, pattern matching, unification, it's just like what we learn as some great features of Haskell or whatever, but why didn't we use it 20 years ago or 30 years ago to, instead of doing Perl or I don't know what, why?
Tinkle is yours.
Well, I don't know. I mean, why, if you had Prolog, why didn't they use it? I mean, it was perfect for such things as parsing, as glue. Maybe you can quickly write a program, no declarations. Maybe, I don't know.
The Japanese used it back in the 70s or 80s for their 5GL project, and that didn't end well.
Yes.
But not because of Prolog, I don't think.
No, but
they're doing a 5GL, just a big,
Which
do
means
everything.
fifth generation languages.
Yeah.
Fifth generation computers, I think they wanted to build.
Yeah, pretty much.
They wanted to build distributed parallel artificial intelligence machine. That would be the ultimate something. And they couldn't even say what it was, but they wanted to build it.
They put a lot of money into it.
Yeah, so the government put money into it, and nothing happened.
It was supposed to have natural language understanding.
Oh, everything.
Hardware support for databases and knowledge bases, all kinds of management.
Semantic web, all kinds of things. Parallel, everything is parallel. Everything is artificially intelligent. Specialized machines for knowledge management. I don't know what. They didn't know what they wanted.
They did get apparently some interesting algebraic proofs out of it that were not easy for a human to come up with.
Okay, all right. There's a huge number of papers about Prolog around 80s, 90s. Huge amount of languages were prototyped. Actually, Erlang was prototyped in Prolog. And Erlang inherits quite a lot from Prolog. Many, even syntax.
Yeah, that's right. There is syntax in Erlang.
Yes, because the creator of Erlang used Prolog to implement the first prototype of Erlang as an interpreter. So I would say yes, this is the use case. You want to prototype an interpreter for your toy language? That's what to do it in. Later you would do compiler, optimization, but first prototype in a scripting language, of course, in Prolog. And that's what he did. Many languages were prototyped as interpreters in Prolog. The first interpreter of Prolog was in Fortran. But that was of course a hard job. But yes, so Prolog needs to be, I think, just like Lisp, it was such a huge innovation that, and it just needs to be studied a little. But I think it's hard to use. It's a scripting language. It's hard to use, just like any scripting language. For small things, it's easy. Once you grow it, you need support. You need type checking, maybe module, better module system. Prolog has modules. They're standardized in the standard. But not all compilers support them in the same way. Prolog has a standard that costs hundreds of dollars to buy if you want to get the standard. It's not. It's yeah. It's just.
That may be a factor. Maybe a factor.
Yeah, I mean.
Kind of went with Lisp in the AI winter as well.
Right.
So maybe we need a Rich Hickey to revive it.
Yeah, I don't know. It's a question. So for me, obviously, it has value to think about this model of computation, and to think about how would you use it maybe in something. Maybe in a different language you can implement a part of it and do something with it. Another take-home message that I would like to give is that domain-specific languages are the only languages that are declarative. So declarative programming is good because you just write your specification and that's your program. For this to work, you need a domain-specific language. Prolog is very good for writing domain-specific languages. So maybe for prototyping, at least. Maybe not for production, but for prototyping. So if you want to play with a language of your own, do it in Prolog and just save time. Once you understand what you want, maybe you can write a C front end or something in Prolog, of course. And then once you really understand what you want, you can start virtual machines and other things. But I would say Prolog is the ideal toy language for toy projects. Scripting language. Thank you.